Thanks, Aline. Oh, thank you very much, Aline. That's only because I've been around a long time. So I've been able to do so many things. And one of the nice things is that I've been able to collaborate with Aline and Marco for many, many years. And I wanted to thank both her and the University of Sheffield for inviting me today so I could talk to you about at least some of the recent things I've been doing with deep nets. And there's a lot more to talk about, but I really wanted to make three main points today. The first main point, as it says in the title, we're going to take a look at why there seem to be these holes and what the deep nets can do. And what I want to do is first give you some general examples, one from vision and a couple from language, about these kinds of black holes that appear in the deep neural networks. And then we're going to dive into a little bit of that in some detail. And then I'm going to try to show about why those seem inevitable, why they seem part and parcel of the architecture of what's going on with the deep networks. So as usual, we should just start out with the typical joke, namely that ChatGPT-4 just wrote this talk, right? So if I ask it, why is ChatGPT like a black hole? Of course, it'll give you an answer, but it won't tell you really why. It's not explainable. So that, in fact, is what I want to go into. What I want to go into today. So let me start with a simple example of one black hole that arises in the visual domain, and then show you an example that comes up in language, a couple examples. Show you why it doesn't seem like it really grasps what's going on in human language, even though it looks like it's very facile in what it does. So we're going to hold off on the cheerleading and try to get to this point about whether they can actually generalize, these systems can generalize, that is, do true inductive reasoning, sort of abduction in the sense that people and children can do. And I think the answer to that actually turns out to be no, and we'll give a very precise sort of geometrical answer to what they can and can generalize about. So as I said, first, an example from vision. So we're going to push them, and when we push these networks, as we'll see, to go outside of what their training data distribution is, and people have looked at that, and some people claim, oh yes, they can generalize outside their training distributions. I don't really think that's true, because then they tend to collapse. So you get a more or less kind of random response that's generated from what they do. All right, and I'm going to try to show you why. So first, as I said, an example from vision. So here's a deep neural net vision example. So you probably all, I don't know if you've all seen this Google Net system, which was done some years back. Here's the structure of the system, a convolutional deep neural network trained on many, many, many images. Here's the training data, all compressed on one, not thousands of examples onto one slide, and then it recognizes images of things from color photographs. So it can recognize, the shark, the nautilus, the cat, a dog, whatever you throw at it, and its accuracy is essentially 100%. Okay, so that's the test data. So these kinds of full color photographs. But now we're going to do something a little bit different. Okay, so it's nearly 100%. All right, but now we'll take a look at something interesting, which is something that people, actually kids, really little kids, can do. Okay, so this is an old study that was done way back in the 1960s. So pictorial recognition, as it says here, as an unlearned ability, a study of one child's performance. Now, this is a one-off study that was done a long time ago, but it's been replicated. And here's the study by saying an unlearned ability. Well, what's the ability? Well, it's this ability that's shown here. So if you go and you look, so kids see examples. You see how old this is? It's a real Volkswagen. I know they're still here in Brazil. They have them in Brazil and other, but or the sneaker or the doll. And then after seeing that, the kid can actually recognize the cartoon outline. And what they did with this kid is make sure that they had not been exposed to the cartoon outline. That's very hard to do because of things like books and stuff. But they've done many control experiments on this afterwards and found that, yeah, sure, it actually looks like that happens, and it's really young. By that, I mean, it's as young as 5 months of age, okay? By then, they already, if they've seen a car in the street, they can recognize the line drawing. And they do it really well. So by line drawings, here's what we mean. So like here, an accordion, an ant, an apple, and so on. You can do this, right? Everyone can do this very easily. They don't have any problems. So then this is a standard image set. So it's Snodgrass and Vanderweer, sort of standard image set of outline drawings. So now the interesting part, I know I'm going a little bit fast, but this is just sort of the preliminary vision example, is let's look at what happens with GoogleNet and this. So let's pick GoogleNet versus humans. So here's, I don't want to hold apart everything. So here's on full color images, they're essentially humans in GoogleNet at 100%. If you do black and white line drawings, so here's the outline of the car, here's the bicycle, here's the Nautilus shell, here's the shark, right? So we're going to give it these, but it's only been trained on this, and that's what and we still have kids do fine. So on black and white drawings, kids as young as a year old do perfectly on this. Now, who wants to guess what GoogleNet does? What's the performance of GoogleNet? That it has to be somewhere between. And you get a beer if you get within like 1%. And you want your beer. What can I do? Yeah, and sure enough, 14.38%. Wow. So there you go. So clearly GoogleNet does not do what human beings do, what infants do. It cannot generalize abductively, really true induction. That's what I'm talking about. There's something that's outside of its data set. It's just not what kids do. There's something's going on that we'd have to actually then have a theory. Wow, how scary is that? We'd have to have a theory of how vision actually works to get it to do this. We can't just, of course we could present it with the cartoon outlines, but the kids don't need that. So that's going to be sort of the main theme of the rest of this talk. So we're going to look at the deep neural nets, I'll call them dNNs. We'll look at ambiguity, and I'll take one of the oldest and maybe simplest examples of that, having to do with flying planes, then look at sequences and structure, and we'll look at, again, one simple example of that. Then I'm going to turn to a third kind of stress test, which is to show that there's a sense in which the deep neural nets are too powerful and not explanatory. That's something that Chomsky has talked about quite a lot, which is you don't want them to easily learn unnatural Martian languages or Vulcan or something, right? And that's something we actually studied when Alina was visiting MIT way back in 2012, before the current era of deep neural networks. In particular, we'll take a look at reverse languages. So there's no human language where you form a question by taking the original sentence and just turning it into its palindrome, for example. The human language does that. There's lots of very simple mathematical operations you could do on human languages as strings, but they never show up as possible human languages. And of course, yet, as you might expect, the deep neural nets can easily learn those, but that's not what you want. You want it to capture the human cognitive fraction of possible languages. You don't want it to be able to learn everything, because people don't learn everything, and that doesn't really happen. And of course, the real thing we want to get at there is why is this happening, right? So, and it happens because the deep neural nets, including the transformers, basically memorize the data cloud that they're given. So we'll just take, whatever that training data exists, some cloud in some very high dimensional space. They basically just memorize that, and they don't fit functions. I'm going to take a very different view. Everybody talks about these nets approximating functions, and we think that's a fine way to try to think about it, but we don't think that's what it's doing at all. Rather, they're doing piecewise, sort of linear union of various parts of the data cloud. And I could ask you, if I give you this data cloud and ask you what the thing outputs at the end, what function is it fitting? I mean, is it cosine of x? Is it and there's no answer because it's not really fitting a function. And as a result, what they get at the end, they can linearly interpolate between what they've seen, but that's all. They can't sort of jump outside and say, oh, I got line drawings. I don't have full color images. So as a result, there will always be holes, and there will always be, as you may know about, adversarial examples you can fool it with. So this is a natural implication that follows from this. So, okay, so there are always going to be holes, and we'll see geometrically at the end of the talk why this shows up. Okay, so let's look at why these holes appear and why it looks like sometimes these ChatGPT does seem to recover something about language structure. We'll see that also is something quite natural. Okay, so we'll start with this. As I said, the oldest example I could find about this, which dates back to Chomsky's, when Chomsky was doing his thesis work way back in 1955. The oldest possible example, and maybe the simplest one you could come up with, just to poke into this a little bit. So here's the sentence. So if I say flying planes can be dangerous, okay? That's the example he came up with in 1955 to show. So that can be ambiguous, right? So what are the two ways you could interpret that? We'll leave aside the non-native speaker so that Margaret doesn't have to get worried about that.
It's right. Flying is an adjective or a verb, right?
Say again?
Whether flying is an adjective or a verb.
Yes. So I could be so flying planes. If I'm a pilot, that can be dangerous. So piloting planes can be dangerous, or it can be that the flying planes in the air
Can follow you.
it might knock into you, right? So those are the two, right? So here are the two analyses. So either you could have that the flying planes are dangerous, meaning someone, that's this pro, flying the planes is dangerous, or flying planes is a whole noun phrase, that's a subject, that those things themselves are dangerous. So what, right? I mean, that's a neither of those two interpretations is really ambiguous on its own. I mean, once you get either one or the other, okay? So it could be either one if I have can be. So, but now you do the thing that Chomsky talks about. So there's two different structures associated with the two different meanings. That's what you want. We're going to look at what ChatGPT does. So the first one is they are flying planes, right? So there's another one that's a little bit ambiguous. Okay, so here's what the August 3rd version of ChatGPT 4 does. That's the latest one I could get. I don't think they've updated it since then, but I could be wrong. You just never know, right? So I give it, I tell it, I don't know, it looks like that's a little small to read. Is flying planes can be dangerous in an ambiguous sense. So that's, as usual, the particular, cues you give to ChatGPT, it really can give a different answer depending upon the way you do this. So I'm going to gloss over that a little bit, but so notice what it says then. Oh, it looks like it's maybe it's doing it right. It says the sentence flying planes can be dangerous can be perceived as ambiguous because it gets those two airplanes in flight or the act of piloting airplanes. To say, well, wow, it really does know what's going on. But now we're going to poke a little deeper. So at first blush, it seems to know, but we're going to actually push into this a little bit. Closer inspection. So I can say, is flying planes are dangerous, unambiguous sentence, okay? All right. So what does it say? So then it says, yeah, adjective use of flying, gerund use of flying. So we say, okay, seems to be doing well, but is that right? So it still thinks, but that's not right. When I say flying planes are dangerous, it should just be the one use. So it got this wrong. It still thinks it's ambiguous. So it hasn't figured out that this is now disambiguated. That's wrong. And when you try to do the check, you set up the context many different ways, it still gets it wrong. So it doesn't disambiguate. And in fact, what this indicates is it's not really doing sort of that structural parsing that I showed at the very beginning. Rather, it's using this semantic embedding in a slightly more subtle way to get at that kind of pattern. And it's really sort of discarded this are versus is distinction. That's been blown away because it's being overridden by the rest of the context. And so if I change it to is flying planes is dangerous, unambiguous sense. And again, the answer should be no, that's not really ambiguous, but it says it's somewhat ambiguous. So it still has that. So it's actually, so I'm sorry, going too fast. So it's very sensitive to that, but it's really clueless. So I say, what does flying planes, this is just another way. What does flying planes are dangerous mean? Okay, it says, well, it's grammatically incorrect in standard English. But of course it's not, really. The correct phrasing is flying planes is dangerous. Because then but it really is quite clueless about it. I ask it another way. Flying planes is dangerous. What does this mean? When someone means flying planes is dangerous, it implies a belief or assertion that engaging in the activity of piloting involves a high level of risk. But then it has this thing about planes crashing and something else about that. So it really hasn't gotten to it. Seems like that's unambiguous. But when I do flying planes are dangerous, what does this mean? What's it going to say? And see, the fact that you say, well, I don't really know what it's going to say means that you see, you don't really understand. This is what it means that the model's not interpretable. That its answer is going to be variable depending upon how you ask it. The phrase, and this is exactly the same answer it gave to the previous one, flying planes is dangerous. So it's conflated those two as far as this goes. So you see, and I actually obliterated, these were all separate chats because it uses, of course, the reinforcement learning context to guide it in its discourse. And I tried to control for that by obliterating those. So these are controlled for that. So sort of the upshot from that is that ChatGPT really isn't doing the parsing and really isn't building the two different syntactic structures, not the way that we think people do, because we can do the actual online experiments to show that people actually do build different structures and try to disambiguate them. Okay. Well, you might say, well, that's just ChatGPT 4. Maybe this isn't so pervasive, but in fact, it's quite pervasive. So as far as I can tell, when you run it through almost all the online, the existing sort of deep neural network based parsers they have around now, it gets the same thing wrong. So here's the Stanford neural network parser. When I say flying planes is dangerous, well, it gets that as a compound, which is what I want. So flying planes as the subjects, that seems okay. That's the flying planes compound. But when I do it for the R dangerous, it doesn't do it correctly. It still makes it a compound. So it doesn't really do the parse the right way. Same thing with the Google neural network parser, which is called Stanza. This is the output from Stanza, where it just says, I just did it with flying planes is dangerous. This is a dependency grammar output. But notice it just says that flying is a modifier of planes, an adjectival modifier. Same thing if it's R dangerous, it does the same thing. So it doesn't distinguish. It collapses those two parses. Okay. So that's that compound reading. It doesn't distinguish. And the same thing with the Berkeley neural parser. It gives the same output structure. Flying planes are dangerous. It has this. It got this right, namely that this is a flying, but it's all just a noun phrase. And when I have flying planes are dangerous, so it's like this. And so if it's is dangerous versus are dangerous, it gives the same syntactic structure. So it's not going to be able to tell these apart. It assigns identical representations to them. And it doesn't get the ambiguous case either. So it just says, oh, that's just, this can is a modal verb. And so it looks like none of those things work properly, which is kind of weird because, you know, like I said, I'm so old that I remember when they used to do parsing versus sort of standard grammatical means, and at least we could do this much and get it right. So it's like we've gone backwards a little bit. So that's odd. And you might say, well, this is just a funny case that Chomsky made up and it's not really going to matter, da 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 da. You can tell that story. But I think actually it will matter. It's going to matter in cases like this. Why should we care about this? Well, here's another. Suppose we decide to deploy ChatGPT in one of these the settings I was talking about in the last talk, you know, like in a medical setting, right? And so we'll have that as a ChatGPT is the front end to replace the doctor. Well, you can have a question like this: growing tumors is dangerous. Uh-oh. Now what? Right? So if I ask it, growing tumors is dangerous, and I say, why is growing tumors dangerous? It's not because the person, you know, the meaning is that the person, you know, growing them in the lab, it's a dangerous process to do, something can happen. No. Of course, it gives the answer that, oh, it's because it's a growing tumor inside somebody that's dangerous. Because it has the growing tumors are dangerous, which is true. If they're growing, they are dangerous to the person. So this would get that meaning wrong because it's, as I said, drop this very simple difference between is and are. And as a result, it just goes off the rails. And if you just trust it completely, you won't know that. So I think that's a real problem. Okay, so there you go. I mean, so it's funny that these kinds of important things seem to have been lost. Let's see if we can see, you know, why they have been lost and what's going on. So let's look at it a little more generally. So let's look at some, what we're going to do is, so this was like an introductory foray into this more general problem. So I'm going to take a quick look at some more large scale testing of other natural language examples, then also impossible languages, and then do a post-mortem on that. And the post-mortem is going to be a geometric look at why this is happening. So we're going to take a geometric look, and by that I mean we're going to take a look at the data and how it's sort of fit by the deep neural networks, keeping the deep neural network, keeping that input data fixed before our eyes. Okay, so before the large scale testing, one other example. So you say you might be unhappy with these kinds of GPT systems, and that's something else GPT-4 doesn't understand. So this is the actual prompt that I'm going to give it. You'll be given a context and questions, and then you tell GPT to answer the question. So here's the context. Trump is not unhappy with Obama. Trump is unhappy with Clinton. Question, is the following statement true or false? Trump is unhappy with Obama or Clinton. Now you can answer that. So what is the answer to that? All you speakers of
I think it's gotta be true.
yeah, it's gotta be true, right? Oops. So it says here's ChatGPT. Trump is unhappy. It's true according to the context because blah blah blah. Logic or is inclusive, meaning the statement is true if at least one of the conditions is true. Trump being unhappy with Obama is true. So yeah, so there it looks like it does right. But the problem is that unhappy is not the same as not happy in English. I don't know if people have thought about the syntax of that, but we can do the same thing here. You'll be given a question, a context and question. The context is Trump is not happy with Obama. Trump is unhappy. So, we did this one, right? Is not happy with Obama or Clinton. So the statement, Trump is not happy with Obama or Clinton. What about that one? How's that different from unhappy? If I say Trump is unhappy with Obama or Clinton, it could be either one. What about if I say Trump is not happy with Obama or Clinton? What does that mean? Yes, because you can't be happy with both of them, right? That's the difference.
Could be just neutral.
Or it could be neutral. But one of them is it could be not happy with Clinton, not happy with Obama. So here it says it's the same as the unhappy case. So that's not really quite right either. Okay. So it just showed me that it got lost. It really doesn't construct the more subtle aspects of English syntax. It looks like it does, and we'll come to that in a moment. And I have an explanation as to why it looks like it does. It plainly does extract some things, aspects of that. So let's look at a more thorough case. So, as people may know, in the last 3 or 4 or 5 years, people have said, well, we've got to probe this behaviorally, the input-output behavior systematically of these deep nets. And we'll do that by constructing some large-scale systems that have so-called minimal errors, as they would talk about it in linguistics. And on one of them, it's got to say, oh, yes, that's fine. And the other one's got to say, no, that's not fine, just the way in, and see how that corresponds to what people do. Okay, and there's been lots of those. One of them is called Blimp. Another is called Zorro. They're doing this now with systems that have been constructed with smaller data sets to try to more attune themselves with the amount of data that kids might actually get, and then see whether they can mimic the yes-no patterns of how sentences look. Okay? Now this is really tricky, and one of the things they test is subject-verb agreement across a prepositional phrase. I'll give you an example in just a second. Now, the thing about this is that in order to do this, to control for all the possibilities, they typically write programs to, they use Python to construct some template structures, and then fill it in with various words and try to control for factors, but they don't really control for all the factors. So here's an example. So here's an example from Zorro that's trying to look for subject-verb agreement across a prepositional phrase. So here's the lies. So notice it's picked this funny noun that it just filled in from the program. So it's done this for many, many nouns. So it has thousands of examples it's going to run through the system. And then here's the prepositional phrase on the floor, on the foot. Again, a sort of funny. And then is flat. And then it wants to test the subject, the agreement is here. As opposed to the problems on the pattern is needed, the problems on the pattern was needed versus were needed, right? So it's going to try to test that agreement. Okay, so let's see, it has lots and lots and lots and lots of examples like this. And what people have done with Zoro and with Blink, they run these tests and they get great agreement. Well, that's all well and good, but there's this kind of subtle problem here. I don't know. Can anybody think? So one of the answers might be, well, the system worked really well in doing some heap of agreement. So they get fairly good scores on this. Not perfect, but with people, but pretty good. But you might think, well, but why is it getting this? You know, what knowledge of language has it itself encoded to get this? And the answer is we don't really know because of the way these systems are trained. The subtle problem is this one. The subtle problem is that when you construct these kinds of databases using these automatic systems to plug in nouns like lies and foot and so on and so on and so on, you can just by accident set up spurious correlations between the subject and the verb you want to agree with. And that turns out to be true in all these big data sets that we've looked at. You can replace any sophisticated syntax with very simple linear rules. I'll show you one in just a second. And as you know, these systems are really good at figuring out sequential patterns. So there's nothing that says, well, maybe this thing just internalized a sequential pattern. There's nothing to rule out that possibility. So here, the problems on the pattern are needed. So S here are no, plural here is. So here's the sequential pattern. So for all those cases in the BLIMP and the other database, the following rule, this rule suffices. The second word ends in S if and only if the third word from the end is are, was, or do. It's like a simple linear regular expression. So how do we know the system just didn't do that? And the answer is we don't. So, and that works for all those tests that they've done so far. So you need a much more carefully constructed test database that's balanced out, you know, eliminated those kinds of possibilities. That's hard to do. And no one's really done it so far as I know. So as far as we know, these systems just could be n-grams on steroids. As far as we know. I mean, I'm just saying, it could be that, of course, that they really are working, but it's also the case that it could be this kind of n-gram analysis.
Shouldn't it not be R worded?
Where is maybe I got this wrong.
The plural formation should be word.
Oh yeah. I just had a typo there. I'm sorry. Thank you for pointing that out. Yeah, R word. Yeah, I guess I don't know English either. I knew something was wrong. Gee, nobody corrected me though. I know, it's so nice growing up. So I only got positive data. I'm just kidding. So we can't. So as you know, with the attention-based systems, the window size for the attention window can be up to 10,000 words long. That's pretty long. So if there's any linear pattern, it's going to be able to pick that out. Okay, so what are these things really doing? So why do these holes exist? So it looks like there are lots and lots of these kinds of holes. As I said, I think there's a kind of geometric answer to this. And so in the rest of the talk, I'm going to sketch out the geometry of what our view is of what's going on with this. It's not it really isn't very much like the classical view of things. So it's going to be like a shift in perspective. So I'm going to see but let me talk about one more thing before I get to that, which is this. Oops, I didn't want to talk about this. I want to talk about this, which is that there have been related to these modern chat GPT systems, which are also called, as you know, attention network systems, because they have so-called attention heads, which can look across a wide sweep of all the words, is that there have been people that have claimed that, gee, they do induce a kind of implicit linguistic structure that is hierarchical in nature. And there's a recent PNS article by Manning et al. from Stanford that discussed that. And my reply to that is that, in a way, that's not really a surprise. It's not a surprise because if what we're doing is starting with say the Axel model is syntactic in nature, but then you throw it into a word embedding, that's going to leave behind at least a residue, like but a foggy residue of what that syntax was. I know that's a very vague statement, a way to put it, but I think that's going to be latently there. And so what these people are really doing is doing the inverse problem of going back from what the, because in the end, what these attention systems do is that they say, oh, the sentence John kissed Mary is similar to the sentence to Mary was kissed by John. So it puts them nearby in some topological space. So it starts out with the sentences down here, and then through this eventually has those near each other. That's what you want. So that in part implicitly has some of the structure. And the way I would diagram that is, so that results from the way that things are masked. So if I start out with something like, he waited while John ate, and then I want to know the representation. I want to know, oh, he can be related to John. That's what was mentioned in the last talk. It's sometimes called anaphora. So he waited while John ate, then he and John can't be the same person. So if I mask John, and then so I wipe that out, and then I ask the system to predict this, then it should say that, oh, I don't want to predict John in this position and have them be linked with the same thing. So in that high dimensional space, he and John are going to be far apart, where he and John are. Okay? So they'll be far apart. So if we have enough data, which there is in this training data, indicates like while he waited, John ate. In this case, he and John can be the same person, but need not be. Then I want to map that in the semantic space to something where they're actually close together. So it's something where these two are close. And so the training data will do that. Okay, so I have training data on both cases. So I have this associated with this kind of structure, and I have that one where they're far apart associated with the other. And eventually I cover all those kinds of possibilities. So it's no surprise that in a way I have a kind of replica, although a very fuzzy one, of what that original syntactic structure was. Okay, so solving that inverse problem is not easy. And so it might not even be well posed, but I think that's eventually what's actually happening. Okay. So that's the my intuition about what the masking does. It eventually is going to reconstruct enough of those syntactic dependencies viewed through a fuzzy semantic lens. Yeah, I want to mention this last and then go on to this geometric view. So here's GPT-4 in impossible languages. As I said, we did this a long time ago with the very old statistical parsers from the days of the early 2000s, which were very different. They weren't deep neural network parsers, but they were essentially, I guess you could say they were almost like decision trees, but with statistical, points in each branch deciding to parse it this way versus this way, but they actually built the parse trees. So we replicated this kind of experiment, which was done with an earlier version of deep neural nets, LSTMs by John Bowers here in the UK. And we did it with the more, the richer attention systems. How does the Chat GPT does? And as I mentioned, if it does well, it's not human. It doesn't have explanatory power because people can't do this kind of thing. And the answer is that, and we use the same data that Bowers used. Okay, the same sort of testing method. So with the original test set with GPT-4 was about 88.4% accuracy, and reversed at 78.2. That's pretty close. We haven't done enough tests to see whether that's statistically significant or not. But it's not so. It's pretty good for reversed sentences. So we again think this is a pretty bad sign that these things are they're also too general. So not only are they not specific enough in that they don't get is versus are, they're also too general. So they sort of failing on both counts. All right. So okay, so that's the first part, which is talked about some of the particular failures of these networks. And now for the last part, to finish up the talk, I wanted to talk about a geometrical view of this, which we think might give some insight into why this is going on. Because people want to talk about explanations. What is the inductive capacity of these networks? So, and our starting point is to take the old Minsky and Papert book on perceptrons, which took a geometrical view to what single layer perceptron networks could do. And we want to extend it to these multi-layer networks. So where there's a number of layers L, and with respect to some clouded data point. And I want to contrast our approach with what I think almost all the rest of the field, aside from a few other people, are doing. So remember, these networks, I want to just talk about a fully connected RNN. So for the moment, forget about transformers. They introduce some algebraic complications, but we'll put those mostly aside. And remember, for the output, we have these so-called rectified linear units, which are 0, 0, 0 to get to a threshold point, and then it looks like this straight, this y equals x line going up. I assume probably people in other networks have seen this. So nothing, 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 and then triple, right? And that's the only, quote, non-linear part of it. There's a discontinuity at 0, right? All right. So actually, let me back up. So here's the sort of standard approach. So each layer of the nodes, you take the input data, and then each layer of the nodes, so you want to think of it as a set of transformations. So it maps that input space to new space, and the next layer to new space. Boom, 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 boom. Right? So it's transformations of the input space. And that kind of leads to this, we change the coordinate system at each point, at each one of those steps. And we think leads to this kind of function approximation view. Sometimes people use kernels, sometimes they use whatever they use. But they really do think of it as function approximation. And the metric's Euclidean. So eventually the new coordinate system is nonlinear because you have that nonlinear ReLU at the end. Fine. And that's why people have gone. And we think that's gotten people a little bit off in one direction. Because as I said, I don't think it's really we're really doing function approximation in the classical sense. So here's sort of our view is that is geometric, which is to think of what are the regions in space, if I have a data point that activates a certain set of neurons, right? So if I have one training point, then a certain set of neurons will fire. I have another training point, maybe it activates the same set of neurons. And so by collecting together that a whole set of neurons that get activated, that turns out to be a polytope, in some high dimension. So there's no coordinate transformation. You keep the input space fixed, right? So instead, we divide the input space into convex polytopes. And some of those will have the training points in them, and some of them won't have the training points in them. The ones that don't have the training points in them, you don't really care about. So each of the convex polytopes can be represented by each layer of the network as a unique and a different set of affine coordinate axes. Okay, each of which distorts the original Euclidean measure. Oh, 8 minutes, okay. So the picture looks like this. We don't think anything's fit. As I said, we think it's just, oh, you have a data cloud here and you fit a linear function to that. You have one here, you have one here, and it's just a union. It's a piecewise union of those. Now, the interesting thing you can do now, so I'll speed up a little bit, is you can actually count which, as you go through a network like this, you can count which, so here's the input X, which of those neurons are going to get activated. So at level 1, 1, 3, and 4 got activated. Here it's 2 and 4. Here it's 5. Here it's 3, 4, and 5. Okay? And this has been done by other people that I referred to here. And once you do that, then what you can do is map that, because on one side of, like the perceptron, on one side you have the active units, on the other side, those red guys, they're inactive. So not all the neurons are active, of course. Then it would be a kind of degenerate kind of network. And what that does is it slices up the space like this. So each one of these corresponds to a single, an input to a single neuron. So one slice is like this, one slice is like this, one slice is like this. And if you look at it in terms of active.
See your point.
Oh, they can't see my pointer. I should point. That's a defect in the. Right. So it slices it up into different units, and see here's the convex little polytope that gets created. And so you can use the mathematics of polyhedral arrangements like this. If it's a shallow network, you can find out what's the maximum number of such polytopes you can make. There's a whole geometric theory of this. There's a huge upper bound on this. So people who looked at neural networks claim, oh, the capacity is really 2 to the n, where n is the number of neurons might go through all the layers. That is a bound, but it's such a gigantic upper bound. It's crazy. It doesn't really tell you what the power of the system is. So let me actually just speed ahead and go to what. So when you do this for a couple layers, you wind up with this picture. So let me just talk about, so if I start with X and Y, and I just project to A and B, that's just the first layer, I get this cut. That's 2 lines. And these are projecting in, so that's a 2-dimensional space. But notice this is impossible, so it's 0-dimensional down here. These are impossible points. When I project up to the next layer, C and D, that actually bends at the next level up, is where they can join and it refracts. So remember I said the transformations are always sort of bending in each layer. So when you do it through 3 layers, you wind up with this, it's like origami, in fact. You can show it's equivalent to origami, with this bent polytope. So that's the only active region. So you can actually analyze it this way. And the next slide shows what a more complex, like a 1-layer system looks like the thing on the left, and 2 layers, you see where they're bent. You get regions that look like on the right. And the interesting thing is that when you do that, you can show that in a situation like MNIST, I want to get my MNIST slide, like this. Let me just, so here's the MNIST structure where you're trying to recognize the digits 0 through 9. So 10 categories. And so you have 21. So you have these 3 layers here, and you have like a 21 by 20, this. square matrix for every one of the digit recognitions, you might think the input dimensions 784, the architecture 64 neurons times 3, 120, 192. So you might say, well, gee, there's 2 to the 192 possibilities, but that's not true. It turns out, and this was done by others, after training, the number of regions you need is only 8,541, which is 2 to the 14th. So that's the actual bound. So most of the neurons are not used. Most of them are used for something else other than maybe for stability. We're not sure, but it's much, much lower. And then what you can do in terms of what the power is once you get those neurons cut into these regions. And again, this is just the same original input space. If I take the convex hull surrounding all those, the only thing that the network can do is interpolate, linearly interpolate between any one of these regions. You can't do anything else than that. So if it so happens that one of the new data points it gets, it's not a training point, is within that convex hull, then it'll do fine. But if it's outside that, it's just going to guess, which is why you get those wacko things that are outside of it. And why you get, so I'll show you, I guess I'll just end with a one-dimensional example, which is just illustrative. This is what the polytopes look like, where we're trying to estimate the function cosine of x. So here's cosine. Oops, I didn't know that's an helps. No one end in that. So this is the actual function fit. So the neural network does really, really, really well. The regions, because it's 2D, are all sort of 1D cuts. So they're just these lines. So at each input layer, so it's just 2 hidden layers and the input layer. So it does a perfect fit. But this is the training data from here to here. So notice what happens outside the training data for the function that it goes off to infinity. It's wrong. So it can't. So see, it's just guessing. So no human being would do this. A human being would say, "Oh no, now it's cosine. So it's going to go like this." But the neural network doesn't do that. And how could it possibly know? So it's not doing real abductive inference in the sense that a person would. Okay. So this, by the way, also accounts for the adversarial type examples, because you can show that most of the training points are going to lie close to one of the edges of one of those polytopes. So it's very easy for it to be perturbed and flipped to the other side, which changes it from cat to dog or whatever. So in this case, as we know, you can get these funny perturbations that change things from, literally from cat to dog or from bus to zebra or something, right? So to end with that, given that on some of these language examples, it doesn't seem to really get syntax, and given that it really is driven entirely by the data set, as it claims to be, it's data set driven. That's what it is. It's not doing anything else than that. It doesn't construct a theory or any other underlying account of what's going on, and that, I think, is the primary problem. So just to end with the joke slide, I guess the joke slide is, don't believe everything you read in the newspaper, especially the Guardian and the New York Times or the one. Okay, so that's the story for today. I know there's a lot more to say, but I'll stop here.